we are going to cover, first of all, this is a new section of Hackfest where we would like to start seeing OSM in a deeper way so that participants understand what's going on underneath between the components of OSM. So it's easier to troubleshoot OSM when you see an error. It's important for you to understand what's LCM doing, what's VCA doing, RO, and everything, so that you start being more independent when operating OSM and knowing how to do things in an easier way. To provide a summary first, we have a bus interconnecting or providing a means for components to communicate in a synchronous way. So this bus is provided by Kafka, and that's where a component can say, okay, I'm leaving this message here. If anyone is interested in that message, it can consume and make something about that. For example, you want to instantiate a VNF or want to monitor, get a metric from the system or something like that, and the NBI component, which is the one that exposes the API, can leave that message on the bus, and the components subscribe to that message or to that topic, because the messages in a bus are organized in topics, takes action and delivers a response. So that response can be read back by the NBI and delivered to the client. So that's an asynchronous message where components are not waiting for each other. They just leave a message and expect the other ones to react. Another way is synchronous communication, where a component talks directly to another component and it waits for a result. So both kinds of communication between software components are useful for different use cases, but it's important for you to be aware of both kinds of communications. The LCM as the end-to-end orchestrator, so most operations are passing through LCM when they are related to lifecycle management or of a resource. It can be a VNF, or it may even be a VIM, a registration, for example. We will see more details later. So LCM has direct communication with VCA, which is the component that controls the configuration of network functions. So it gets inside the network functions and configures them. Today, our main element there is a UU controller that through the way of charms, which are pieces of software that can manage the life cycle of applications and the state of these applications. Through these charms, we configure the network functions. And then we have RO, which is the resource orchestrator, which provides a way to interact with VIMs and manage everything related to virtual machines. It communicates with cloud platforms like OpenStack. It communicates with SDN controllers. It communicates with WIMS as well. I mean, the Wide Area Network Infrastructure Manager, which controls the inter-data center connectivity. We have the monitoring platform, MON, which collects metrics from the system, from NFBI as well, to show the state of the network functions, and also monitors some connections, like the connections to the VIM. It monitors the status of the virtual machines as well, and we will keep adding things to MON so that the state of everything that is relevant is captured by that component. We have the policy manager, which takes actions after some state. For example, it can provide automatic scaling in or scaling out of network functions after a metric has passed a threshold, or can just throw an alarm whenever a metric has reached some level. We have a new component here, which is the placement module, and we'll add some automated decisions for where to deploy and which beam to deploy given network functions that require has some needs for specific latency or jitter or bandwidth or cost of the infrastructure. We have the NBI, which provides a way to interact through a REST API with the system. So that API is leveraged by the client of OSM, the CLI, or the dashboard. Both use the same API, and you can use it directly as well. We have the databases. We're missing here the MySQL database, which is one shared by many of these components. We have the NoSQL database, which is provided by Mongo. We have object storage. Depending on the implementation, it uses the file system or can use external storage system. We have Prometheus as time series database. So everything that Mon collects goes to Prometheus and is stored there. We have an authentication module through an internal backend or through a Keystone backend that provides identity management and assignment of roles in the system. When dealing with the creation, modification, deletion of users, projects, roles, we have the MBI, which receives the call of what we want to do. And then if we are using the default configuration of the system, which is an internal backend for identity and assignment, then all of this identity information is stored in a common database, which is provided by Mongo. So the system can go and ask for the privileges and the users there in that database. Or we can, by configuration of the system, switch to Keystone, and that provides other use cases like being able to integrate with LDAP for external database of users. And it, of course, has its own database for identity and assignment or for assignment only. And when I say assignment, I'm talking about roles in the platform, privileges. When uploading packages, what's going on when we upload a package? When we, for example, do a OSM BNF create or OSM BNF package create, which are equivalent, or we do a NSD create or a NS package create, when we are uploading a package in the dashboard directly, what's going on? So the API call, it reaches NBI. NBI then translates that call to a package storage in the storage that we have depending on the installation. So this would be a local file system, a Docker volume, any storage backend provided by Kubernetes, or it will depend on the installation of the OSM environment that you have. And once that package is stored, then all the information from the descriptors is stored in MongoDB, so that you can later query that database and will find everything related to what is in the descriptors of the DNF, of the network service. It will be there. When we want to start launching network services, we need a beam, right? So one of the first things we do in OSM is create a beam. And which components interact with each other when we create a beam like this? For example, OSM beam create, and we specify the user password and the URL for OpenStack, for example, or we do this same thing through the dashboard. When the NBI receives the API call, the information is stored in MongoDB. So the beams are there in Mongo. Registration call is taken by LCM, and LCM drives it to Arrow. And Arrow stores that information in its database provided by MySQL, because Arrow is the main component interacting with the beam. So it needs to be aware of the beams that are created in the system. And continuously, in parallel, Mon is querying the common database to look for active beams. So whenever it finds an active beam, it then gets its status. It queries Keystone first, I mean, to get a token, of course, but then it queries the list of projects to find that the beam is valid, that is up. So Prometheus, at the same time, is looking for active metrics in MON. And Grafana is doing the same for Prometheus. So at the end, when you create a beam, and the beam is stored in the Mongo database, its status, I mean, its health will be queried, and the metric will appear in Prometheus. Then we have the creation of a Kubernetes cluster. This is brand new in release 7. When you create a Kubernetes cluster, in a similar way to the beam, it goes and stores that information in the common DB, then registers through LCM the Kubernetes cluster, and LCM interacts directly with the Kubernetes cluster to prepare a controller component and Helm element to then manage lifecycle of pods, and it goes to VCA to prepare Juju bundles, which is a way to deploy containerized network functions in OSM. So we have these two happening in parallel. We don't have a row here, as you can see. And we don't have MON yet looking for the active Kubernetes clusters and monitoring, but this will be part of release 8. When we instantiate a VNF, what happens in OSM? What happens is the API call is received, then the information for that network service instance is stored in Mongo. I mean, you have not only the descriptor loaded, but you have now the instantiation parameters that were provided, that were fed during instantiation time. So this is the instance. And then, as soon as the information is stored in CommonDB, the life cycle starts. So this is maybe the main function of LCM to create a network service, right? And if it's a virtual machine-based network service, then it goes to a row, and a row goes to the beam and makes all the appropriate calls to Neutron, to Nova, if it's OpenStack, or it can go to a public cloud if the beam is public, or it will go to the VMware components if the beam is VCD or Bio. So it takes care of instantiation and replies back to LCM so that LCM knows the status and can report it. In parallel, MON is always looking for active virtual machines instantiated as part of VNFs in the common DB, and gets, in this case, the active the status of the virtual machine, so that it says up or down for each virtual machine, and that can give us an idea of if a network service is up or down, basically. Then we have a KNF instantiation. Well, we can call it KNF because it's a containerized network function based on Kubernetes. We can call it CNF because Kubernetes is the only way of deploying containerized network functions today. So KNF or CNF today is more or less the same in OSM. When you launch a network service that is modeled for being deployed in Kubernetes, similar things happen compared to the VNF, but I mean, it first stores the network service instance information in the common DB, but then it starts the lifecycle management through different components that are not a row. We have two cases here, two mechanisms for deploying containerized network functions in Kubernetes. We have the Juju-based deployment, which uses Juju bundles, depending of the model of the descriptor of your CNF. If you're deploying that way, then VCA will take care of the instantiation through the Kubernetes cluster. And if you are doing it through Helm charts, again, that depends on how the descriptor was specified. Then it will go straight to the Kubernetes cluster and deploy it using Helm. So again, under construction, we have the monitoring part to look for active pods and get the status of the pods so that we can more or less know the status of the Kubernetes network function that is roadmap for release 8. Then we have instantiation with primitives. Primitives are like actions that are run into the network functions so that we produce a new configuration, for example, or some change in our network functions directly. So we have day 1 primitives or day 2. Day 1, they run automated after instantiation. So aligning to the NFV vision, we are not looking only to orchestrate instances and that's it. We want to orchestrate the instantiation of these functions, and then we want to configure them so that they are ready to provide the services that our operators need them to provide, right? So that's day 1. Day 1 are every configuration that is needed so that the network function starts with the basic configuration. And day 2 are on-demand actions that are asked by the operator to request some changes, to request maybe scaling, to request some monitoring of the network function, of the network service. So depending on the type of primitive, we have different components interacting. If it's a day 1 primitive, it runs automatically after instantiation. It runs in LCM. And what it does is mainly, this is the main path through VCA. So through VCA, which is a UU-based, would be a UU-based primitive. I mean, it would be a charm. It would go to the network functions, either if they are virtualized or virtual machines or containerized. It goes and interacts with the network function directly and produces the changes. Okay, so it does so through SSH or by communicating with an API that is being exposed by the network function to achieve this. We have another case which just implements a specific use case through Helm charts, which produces, for example, a Helm upgrade, which is changing the version of the Helm chart, I mean the set of pods that are running in your application, and that's considered again a primitive, and it's more tied to a day 2 primitive. So in day 2 primitives, they are called on demand through the API. They are stored in a common DB, and then they are requested to LCM. So if the day 2 primitive is the main uses the main path, I mean, it's a charm, then it goes through ECA in the same way as the day 1 primitive. And if it's a Helm based, then I mean the specific Helm upgrade case, then it goes through directly to the Kubernetes cluster. Instantiating with placement. If you instantiate, I mean, any of the cases that we already seen, but you use the placement platform, which will be available soon, then before instantiating, it will ask for placement component to provide the right beams for instantiation. And then it goes and instantiate through a row or VCA as usual. Okay, so it's like an intermediate step. Instead of going straight to instantiating in the given beams that the user wants to instantiate, it goes and asks if that beam is the ideal or if the placement platform instructs the system to use a different beam. Collecting DNF metrics. We have 2 types of metrics that we can collect in OSM. We have the metrics that come from the NFBI, which are provided by the beam. In the case of OpenStack, for example, it would be by Gnocchi API. In the case of VMware, it would be by VROps APIs. In the case of Amazon, it would be CloudWatch, and so on. What MON does to collect metrics that come from an API, I mean, basically CPU, memory, disk, and networking information from interfaces. It continuously looks for active BNF with metrics. I mean, BNFs that were modeled to use metrics or to gather metrics. And this needs a specific information in the descriptor so that metrics are collected. So it continuously goes to the common DB and asks, I think that the default is every 30 seconds. It looks for metrics that are requesting, BNFs that are requesting metrics. So then if it finds a descriptor that it needs metrics, then it goes to the beam, collects these metrics, and stores them in Prometheus. How? Well, it exposes them in a component called exporter, which is basically a Prometheus way of storing metrics in a temporary way so that Prometheus itself can go and collect them. The way Prometheus works is by going to these targets and collects the metrics that are in there before they are replaced, because they are updated all the time. I mean, MON is not storing these metrics directly. It exposes them in a Prometheus format temporarily, and it keeps replacing them, and Prometheus is the one responsible of querying all the metrics that MON is exposing. And that's the way that Prometheus stores, and this is also a database, so it stores all the metrics in a cumulative way. And then Grafana can read and present these metrics accordingly. When you're collecting metrics from a BNF, I mean directly, without passing through the beam, and you want to log in the BNF or consume an API of the BNF and get a KPI that is specific for the BNF, instead of going and asking the beam for it, it goes to VCA, because nowadays we are using UU metrics from VCA, which is a way of collecting metrics continuously using UU. So it's a sort of charm that runs continuously and collects metrics every 5 minutes. But since it's fixed every 5 minutes, we are trying to evolve this to a different method, which would be to implement an independent exporter for BNFs. But before that, this is the way it works. Instead of MON going to the beam to collect the metrics, it goes to VCA. And of course, you need to previously have built a charm that goes and runs commands in the BNFs to expose the metrics in the UU metrics way, and MON goes and reads them and stores them in the exporter, and Prometheus does the same. Alarms and autoscaling. So I mentioned before that there is a policy manager. This policy manager component has two options, two implementations today. So let's see. If you have alarms configured in your descriptor, what MON does through its MON evaluator component, it looks for these alarms that are stored in CommonDB, because when you model a descriptor with anything, that information goes to the CommonDB. We saw that before, right? So MON goes continuously looking for alarms configured at the BNF record. And if it finds alarms in CommonDB, then it queries the metric values actively, continuously, goes to Prometheus and looks for these the metrics that are being associated to each alarm. And if the threshold is crossed, then it depends. If the alarm was configured just for launching, for notifying a webhook service, which is one of the implementations we have, then Paul launches this notification to the webhook service. But if the alarm was looking for scaling in or out, then it goes and puts a message that LCM consumes to instantiate a new a new network function or the scaled virtual machines that are needed. So again, it depends on how you model the VNFD. MANO evaluator, what it does is compares the value of the metric that is in the alarm with the actual value, and if there is a threshold crossing, then it triggers scaling or it triggers a notification. Then we have a new service which is called a MON dashboarder. What it does is it continuously looks for new projects in OSM or new network services with metrics. And what it does, it creates a dashboard in Grafana automatically. So you create you have, for example, the admin project. Then you will find an admin project dashboard in Grafana, which lists all the network services you have, lists the VIMs you have, lists the status of your network services and everything. So it continuously deletes obsolete dashboards in case a VNF is deleted. And it also creates a default network service dashboard with sample graphs whenever a network service is created. So this was added to enhance usability of metrics in OSM, so that you don't have to go manually look for them at MON or at Exporter or at Prometheus API. You can just visit Grafana. You don't even have to create your own dashboards. It will be automatically created. Okay, so those are maybe the main operations in OSM. And what we wanted to do is provide provide an overview on which components do what in OSM. This is open to suggestions, to enhancements, because we would like to cover most scenarios and in the most accurate way. This is useful, as I was saying, for troubleshooting. So don't forget that a general approach for troubleshooting in OSM when you receive an error in anything, I mean, in the VIM, in a network service, is to show the instance. Use the network service show, use the VIM show command, because those commands give you usually the details you need for knowing what's going on. Besides that, since you already know with the diagrams already presented which component does what, when you are launching a network service, for example, and you receive an error when launching your network service, you should know that you launched your call, the NBI should have received that call and should have sent a call to LCM. So the first component I would look into, it would be LCM, right? And if LCM shows everything okay, then I would go to RO, which are the main components in the path to instantiating things at the VIM. So LCM, then RO. And that applies to anything else. So what I was saying is, knowing which component do what, you can troubleshoot by looking at the logs of each Docker container or each pod in the case of Kubernetes installation.
First, we have to know the main requirements to install OSM in just a single host or a virtual machine. Once you have prepared the host with these previous requirements, all you need to do is just to download the installer with the OSM release 7 and make the installer executable. So with these steps, we are ready to start our installation. For installing OSM, we offer two main options. The first option is to run using Docker Swarm, and we have released a new method of installing OSM over Kubernetes. So installing OSM over Kubernetes, we have two options too, that is listed below. We have the default option with a cluster of Kubernetes, and we have another option using UU charms. So if you want to know or get more information about the different method options we have for installing OSM, we have official documentation at this link that will show you now. So this is an important site where you can have information we are updating for OSM release 7. Here we have the main requirements for installing OSM. We also have different options if you want to use a Vim emulator, if you want to enable full management features. Also, we have documented the way we install OSM over Kubernetes, how you check your installation after the process of installing, using Docker Swarm or using Kubernetes. Here in this slide, I'm showing the scenario of our installation over Kubernetes. Here, we will deploy OSM in a single host running a single Kubernetes cluster, as shown in the diagram. We will have to download the installer, and then this installer will install different packages to run a single node Kubernetes cluster, and it will deploy the different objects on it. So inside this cluster we will deploy, there will be three main namespaces or virtual clusters. We will have a kube system namespace, monitoring, and we will have the OSM namespace. Inside each namespace, we will have pods created, and inside each pod, we will have a container running on it. So here, I just download the installer and I made the installer executable. So now I'm going to run the installer, check that this command have the option -c-kas. This is to tell the installer to run OSM over Kubernetes like a container framework. So I'm going to run this script. So the process of installation is starting. So we want to wait some minutes. In a normal installation, it will take like 15 minutes. During the process of installation, we will be asked to confirm if we want to install all of these components. So we just say yes. Okay, and wait until the script is finished. So to know if the installation is finished, we will receive a message at the end that says done. So right now we're going to check the Kubernetes installation first, then we're going to test the OSM client, and finally we're going to access to the user interface of OSM. So first, we want to know or explore how the Kubernetes cluster was installed. So for this, we're going to use this command kubectl. So first, we're gonna see how many nodes we have. The result is expected that we have only one node that has the role of master, and the status is ready. So right now we're gonna list the namespaces created in this cluster. So here we see 5 namespaces, but in the previous slides I only mentioned 3 of them. because the namespace default, kube no list, kube public, we don't use it, but are created by default as the kube system. And for OSM, we need a namespace. We have configured this namespace because there are created all the components for our OSM platform. So if we want to explore all the pods that are created in all the namespaces, we execute kube get pods, all namespaces. In this, with this command, we'll have all the information of all the pods created. For example, we only have pods created on the namespace kube system that are pods that have all the resources for the administration of the cluster. And we have different pods created on the namespace OSM. We have Kafka, Keystone, the user interface, Mongo, MySQL, Prometheus, and different other pods that we have that is necessary to run OSM platform. So if we want to get detailed information of the resources created in a namespace, we can execute kube get all in the name of the namespace. For example, if we want to know all the information about the namespace kube system, we run this command and we have information about the pods that are running, the state of these pods, and also the service that is created, and more information. If we want to know about all the resources created on the OSM namespace, we execute kube get all dash n OSM, and we have all the information of the pod created that the status are running. We have the name of the services created, deployments, and for example, we have information about some services that are exposed. For example, the user interface is exposed to the 80 TCP port number. So later we will want to check this access. And if we want to have a specific information information of a specific pod, we can get that information with this command kube describe pod. Here we enter the name of the pod, and we have to indicate also the namespace. So in this case, the name of the pod is different in each scenario, so we have to replace this name. So for OSM, the pod for the user interface is this, so I just copy that and execute this command. So here we have different information about this specific pod. Also, in the last part of this output, we have the different events, how the pod is created, and finally it finished with the starting of the container that is related with the user interface. Okay. So this is so just some commands in order to explore and to check if the Kubernetes cluster was installed correctly. Now we can test the OSM client in order to interact with our OSM platform. So first of all, we can test with this command osm-help in order to see all the options we have for this OSM client. So if the OSM client was installed correctly, you will have to to get this information. Okay. Now we're gonna test a command. We're going to check the user created in this platform. So just execute OSM user list, and we see that we have only one user created, that is the admin user. So the last part of this hands-on is to check the access to the OSM user interface. So for this last step, or you have to go to this address. Just replace it with the IP of your virtual machine. You just use the admin user, the password admin2. So here we have the OSM platform, the user guide. Here we have different options to create network services instance, to add some Bing accounts, and more options that will be exploring in the next hands-on.